of Department of Mathematics, Sardar Patel University, Semester 2. Good morning, good afternoon, good evening, or good whatever time you are watching this video. So, some of you requested that you have problem with the last section, that is Hilbert Smith operators of functional analysis, and you wanted some revision. So here is the series of videos that we'll probably make on this section. So let us first start with the definition of Hilbert Smith operators. In this video, we are just going to see definition and examples, no results. Further results will be in the next video. So let us start with the definition of Hilbert Smith operator. So these are my notes. You already have it. So let me explain it here itself. So what is Hilbert Smith operator? So first we need H to be a separable Hilbert space. So this is important for a Hilbert Smith operator. This thing is important, that we need a separable Hilbert space. What is a separable space? It has countable dense set. So and we have seen three equivalent conditions, that if it has a countable dense set, then it has a countable orthonormal basis in unit 1, if you recall. So here we need a countable orthonormal basis, and that is why we are requiring this condition, separable Hilbert space. So let H be a separable Hilbert space and T belongs to BLH. So here we are assuming already bounded linear function. So T belongs to BLH is said to be Hilbert Smith operator if this sum is finite. That means this series is convergent. Summation n equals to 1 to infinity TUN norm of TUN square, that is finite. So and what is UN? UN is where UN is any is some orthonormal basis for H, right? So once again, let us recall, let H be a separable Hilbert space. Separable because we require the condition it has countable dense set. Because of countable dense set, it has countable orthonormal basis. Then only we can list like this. We can take the summation n equals to 1 to infinity, because it is countable. So and Hilbert space also. This is also important. We cannot take C00. So completeness is also there. So it is defined only on Hilbert space, not inner product space. So let H be a separable Hilbert space, and T belongs to BLH, bounded we are assuming, is said to be Hilbert Smith if summation n equals to 1 to infinity norm of T and TUN square, that is finite for some U1, U2 and so on, orthonormal basis for H. So this is the definition. I hope it is clear. Very simple definition, only one condition, but we have to remember all these conditions, because when we try to give examples, we have to take care of these things. It must be a separable space. It must be Hilbert space. Completeness is also required. T must be in BLH before we start giving examples. So let us start now with some examples. So for examples, before we give T, note that we need so many things. First, we need to consider Hilbert space. That is a separable. That is the first thing. Secondly, we need to choose an orthonormal basis also before we define what is TUN square. And then we have to define T and check this condition, whether this condition is satisfied or not. Right? So let us consider separable Hilbert spaces. We know examples of Hilbert spaces which are all separable, we know. Right? So let us start with some examples. So first let us consider finite dimensional, very easy. So let us consider some examples. Let us consider first, let us fix H equals to Kn. So Kn is a Hilbert space, Kn over K. So where K is R or C. So either it is Rn over R or it is Cn over C. So this is first we have fixed Hilbert space. And before we give definition of T, we also need first to fix basis. So we need an orthonormal basis. So it is n dimensional. So any orthonormal basis, let us consider, we know this is standard orthonormal basis, which we also denote by E1, E2, En and so on. So let me denote here by U1, U2, Un and so on. So this is orthonormal basis for Kn over K. Because if you see the definition, we need a Hilbert space, separable Hilbert space and orthonormal basis. We need a separable Hilbert space and orthonormal basis. Then now we define T, which satisfies this condition. So this is orthonormal basis where uh, what is UI? UI is this 0 0 and so on, 0, then 1, then again 0, and all others are 0. So where is this 1 is in the ith place, so u1 is 1 0 0 and so on. And so okay, so now we have to define T in BLH. T belongs to BLH, that is T belongs to BL Kn, right? So how do we define T? What is the condition that we need? Let us check here. We need this summation n equals to uh, 1 2. So I have taken n here, so let me take I here. So summation I equals to 1 to n. And what is the condition? T ui square. So this is the sum, if you recall, right? Summation n equals to 1 to infinity if it has infinite orthonormal basis u1, u2, and so on. T norm of T un square. So here we have orthonormal basis consists of only n elements. So we have I equals to 1 to n T ui square, norm of T ui square. Now our condition is that this sum should be finite. Now how should we define T? So we define T from H to H, that is T from Kn to Kn, H equals to Kn here. And how do we define T? T of, let us say, x1, x2, and xn. And we have to define this to be uh, such a way that this should be finite. But this is anyway finite because norm of T u1 square plus norm of T u2 square plus up to norm of T un square, that is only a finite sum. Sum itself is finite here, as you can see. So whatever I define here, it should be a linear map, of course, bounded linear map. And then it is Hilbert Schmidt, as we can see, because this sum itself is finite. We have to worry about convergence of this series when it is infinite sum. If the number of terms itself are finite, the sum itself is finite. I hope this is clear. I'm not going too fast because I do not have much experience giving lectures this way. Based on your feedback, that is how third sem will going to start from Monday onwards. Anyway, so I can define it to be anything. I can define it to be identity. I can take it x1, x2, and xn as it is. I can also define like this x1, then let us take x2 by 2, and so on, and then xn by n. I can define like this. So again, it is kn to kn, right? I can also define another example again like this, or this equals to, I can take x1, then I can take 2x2, then I can take 3x3, then I can take nxn. Any linear map, any bounded linear map uh, on from kn to kn will be Hilbert Schmidt because the sum itself is finite, right? So this is what our first remark is. So let me write a remark here in the next page. So we have a lot of examples if we define on finite dimension. So any T belongs to BLH if where H is finite dimensional, where H is finite dimensional is Hilbert Schmidt operator. Yeah, I'm slow with this initially. I'll get used to it. And you know, this is not how I write in the classroom board. My handwriting are much better than this. Even in KG, it was better than this. So yeah, so any T belongs to BLH where H is finite dimensional is Hilbert Smith because the sum series is always finite dimensional Hilbert space. The basis itself is finite. But when someone asks to give you an example, we should give an example, particular example. It's not that okay, any T like this. Once we are asked to mention example, always give a particular example. Suppose T from C3 to C3, and give an example like this: T of x1, x2, x3. This is equals to, let us take x1 plus x2, x2 plus x3, and x3 plus x1. Something like this, some bounded linear map. One has to be sure that it is bounded linear. And yes, this is Hilbert Smith, because if you take the sum, you can check also. Summation uh, n equals to 1 to here 3, and then this is T un square. So this is nothing but T of u1 square plus norm of T u2 square plus norm of T u3 square. So what will be this? T of u1 is 1 0 0, x1 is 1, other two are 0, so it will be 1 0 1. So norm of T, this is nothing but norm of 1 0 1 and square, and plus T of u2 is x2 is 0 1 0, so x2 is 1, other two are, so this is 1 1 0 square plus T of u3 square, u3 is 0 0 1, so x3 is 1, so this will be 0, this is 1 1, so 0 1 1. Anyway, this sum is finite, just I am computing one example. If you want to compute this sum, what is it exactly, then this. So what is the norm here? Norm is root 2, but here there is a square, so this is uh, 2 plus 2 plus 2 is 6. So sum is finite, and so this is Hilbert Smith. Any finite dimensional Hilbert space, this is any bounded linear map is going to be Hilbert Smith. Okay, so now let us consider example on infinite dimensional Hilbert space. Yes, remember infinite dimensional Hilbert space, so we cannot take C00. So let us take another example. Let us consider H equals to L2. So this is the example we know, and we have to fix orthonormal basis over K. So L2 over K, where K equals to R or C. So if I take R, then I consider real sequences in L2 over R, and otherwise sequences of complex numbers in L2, right? So let us fix orthonormal basis. So again, the standard orthonormal basis u1 u2 u3 and so on, right? So where u1 is 1 0 0 0 and so on, u2 is 0 1 0 and so on, and u3 and so on, right? So this is orthonormal basis. And now let us think of some t belongs to BL L2 BLH. So H equals to L2. T belongs to BLH. Let us define this. So x t of x1 x2, suppose we have a sequence in L2. You know how this sequence in L2 will look like, what condition it satisfies. Okay, so we have sequence and we have to define like this. But let us consider some standard example which comes to our mind. What example comes to our mind? Always think of some easy example. This is zero map. So t is 0, so everything is 0 0 0. In this case, what will be this sum? N equals to 1 to infinity norm T un square. This will be nothing but 0, which is, again, this is, so zero map on infinite dimensional Hilbert space is a Hilbert Smith operator. Okay, so 0 is always a trivial example. It works almost everywhere. And now what about identity? So let us consider another example. So this is there. Now consider t equals to I. Identity. In identity, what will be our situation? We have this condition. Summation n equals to 1 to infinity t un square. T un square is nothing but now I un square, norm of I un square, but which is nothing but summation n equals to 1 to infinity I un is nothing but un. So norm of un square, which is nothing but norm of u1 square plus norm of u2 square and plus so on. So this is 1 plus 1 plus and so on, which is not convergent. Right? This is an infinite sum. So if I take t equals to identity, then it is not going to be a Hilbert Schmidt operator. Identity works well with a finite dimensional case, because you can see finite dimensional as we see here. This is the first example. I can take identity here. T equals to I, x1, x2, xn. I can define it to be x1, x2, and xn, so on. So identity works here because here the sum is finite because, sorry, so this basis has finite number of elements. But here it does not work because the sum is infinite. If I take identity on L2, this sum is never finite. So identity operator on infinite dimensional Hilbert space on L2 at least. This is not Hilbert Smith. So identity does not work. So then what are the examples that we usually compute? So one example we know, we have seen some standard examples. So let us try like something like this: x2 by 2, x3 by 3, x4 by 4, and so on. Right? So examples like this. So this we know this is a bounded linear map. You can check it is a good exercise if you are practicing. Okay, so now we have to check whether this is Hilbert Smith or not, whether this will work as an example or not. So I can consider this example as this as second example. First is so many examples on finite dimensional, and this I can consider to be a third example. Right? Let us check whether this works or not. So what we have to check? This sum again. So summation n equals to 1 to infinity norm of tu(n) square. This is nothing but t of u1 square plus norm of t of u2 square plus, I'm writing like this. You can always compute directly itself from this notation. There is no need to write like this, just for understanding. Now what is t of u1 square? So if I take u1, 1 0 0, and so x1 is 1, others are 0. What is t of u1? Again it is 1 0 0 and so on. So what is the norm of that? 1 square, so that is 1 plus. Now what is norm of t u2 square? What is t of u2? If I take u2, 0 1 0 0 and so on, what is t of u2? So t of 0 1 0 0 and so on. So x2 is 1. So t of u2 is this will be 0. X1 is 0. So this is 0, 1 by 2, and all others are 0. So what is the norm of 0, 1 by 2, 0 0 0? So that is again 1 by 2, right? Plus 1 by 3. Oh, but here there is a square. So we have 1 by 2 square. Again, t of u3 square. So this is 1 by 3 square plus 1 by 4 square plus and so on. Right? So what is, let us consider what is t of u3. T of u3, take u3. So x3 is 1, all others are 0. So it will be 0, 0, 1 by 3, 0, and so on. What is norm of this? So mod of 0 square plus 0 square plus mod of 1 by 3 square plus and so on, and whole raised to 1 by 2. So 1 by 3 square and raised to 1 by 2. So norm of this is 1 by 3. But we have norm of t of u3 square. So this is 1 by 3 square. So what is this? This is nothing but summation n equals to 1 to infinity 1 upon n square, which we very well know this series is nothing but the sum is convergent, and it is pi square by 6. Right? So this sum is also finite. So this is an example of a Hilbert Smith operator. Right? This we have seen, one of the standard examples. So whenever we define something like this on infinite dimensional Hilbert space, we have to worry about this. This sum we need to have is finite. So here I have taken all these elements x1, x2 by 2, x3 by 3. But this gives an idea what is an easy way to give an example. Suppose I take only finitely many non-zero and then all others are 0. Then only finitely many terms will be non-zero in here. So I don't have to worry about the sum. Okay, so let us consider what I said. So let us consider fourth example. Okay. So let again take h equals to L2 and L2 over K, R or C, right? And we take orthonormal basis U1 again, U2, U3 standard orthonormal basis for L2. And now let us define T from L2 to L2 by uh, T of x1, x2, x3, 0, 0. Sorry, this is a general element. So T of x1, x2 in L2. And now, how? Suppose if I define like this, only x1, T of this is, and rest others are 0. Clearly, you can check this will be a boundary linear map. See, I'm taking x1, not 1. If I take constant term here, it is not linear map. So x1. So this is boundary linear map. Now, is it Hilbert Smith or not? So I have to check this sum. Summation n equals to 1 to infinity T of un square. So again, T of u1 square plus T of u2 square plus and so on. And T of u1 square, when x1 is 1, all others are 0. This is 1, 0, 0, and the norm is 1. Square of its norm is also 1. Plus T of u2, when x2 is 1, all others are 0, but here there is no x2, so that is 0. Okay, 0 plus T of u3 square, norm of T of u3 square. So u3, when x3 is 1, all others are 0, but there is no x3 here, so that is going to be 0. When x1 is 0, everything is 0, so this is 0. So the sum is 1. Again, this conversion. So this is another example of Hilbert Smith operator on infinite dimensional Hilbert space. So this works. So from this, now we can define such modifications we can do. T of x1, x2, x3, and so on. We can define it like, let us take two terms, x1, x2, then all others 0. Again, that will be 1, and then 1 plus 1, 2. So this again is Hilbert Smith. We can take finitely many non-zero terms. So we can define actually a sequence of Hilbert Smith operators here. Remember, this will be useful somewhere. If I want to define one Hilbert Smith on L2, I will consider this. If I'm asked to give another Hilbert Smith operator on L2, I can consider this. I can call it T2, x1, x2. Third example, call it T3 from L2 to L2, defined as T3 of x1, x2, x3, and so on. I define to be x1, x2, x3, and then others are 0, 0, 0, and so on. I can define T4 every time any Tn, only first n are as it is, all others are 0. The sum is anyway going to be finite. Right? So we can create a sequence of Hilbert Smith operators like this, which might be useful somewhere. Okay, so another example, let us again consider h equals to L2. 0 is there, identity is not there. Such examples work. X1, x2 by 2, and also we have seen this one. So this is another example. Something where the terms are only finitely many non-zero. We don't have to worry about this sum. Okay, so another examples. You remember we have T is to be right shift. Some standard examples we have seen. And S is a left shift. So I leave this as an exercise for you to check whether these are Hilbert Smith operators or not. And any other example which you can construct. You can post WhatsApp me, or you can post in Google Classroom if you find example is good. Even if you have doubt, you can post in Google Classroom. We can discuss together there. So I hope this is clear. Just go through this once again, and if you have any doubt, you can contact me anytime. Thank you.